Good afternoon, and welcome to ThermoLive 2017, a two-day online event for electrical and mechanical engineers hosted by Electronics Cooling. I'm JJ DeLille, Executive Editor for Electronics Cooling, and it's my pleasure to introduce today's presentation, Thermal Design and Integration Considerations for Thermoelectric Devices in Cooled Optoelectronic Packages by Phononic. It will be approximately 35 minutes, followed by a short question and answer session. You may ask questions at any point during the presentation by entering them into the Q&A panel. We will get through as many questions as possible in the allotted time, and all questions can be found on the ThermoLive website following the event. The slides can be downloaded directly from your audience console as well. Simply click the content icon at the bottom of your screen. Our presenter today, Alex Guichard, is a Senior Product Manager of Optoelectronics cooling products at Phononic. He has several years of experience working with customers to design, develop, and engineer new products in the field of solar, LEDs, and thermoelectrics. So, without further ado, over to you, Alex.
Thank you, JJ, and thank you everyone for tuning in. Today, I'm going to show you how optoelectronics products are facing new thermal challenges and how thermoelectric coolers in concert with smart package thermal design and integration can address those challenges. First, a brief word about the company I work for. Phononic is a thermoelectric device and product manufacturer. Our headquarters and device fab is located in Durham, North Carolina, and we have sales offices as well as manufacturing partners of our end products throughout the US and Asia Pacific. We've also been recognized as a CNBC Disruptor 50 company for 2 years in a row. In this presentation, I'm going to first describe generally why and how thermoelectric coolers, or TECs, are used in optoelectronics packages for cooling and temperature control. Next, I'll talk about some trends we've noticed in laser package design with a focus on how those trends are creating new thermal challenges for optoelectronics component designers and integrators. And then finally, I'll show some new technology examples of how we can tackle those new and increasingly stringent thermal challenges. So, how do TECs keep lasers cool? Well, a thermoelectric cooler is essentially a solid-state heat pump that can transfer heat away from a heat source to keep it cooler than ambient temperature. TECs consist of 2 parallel plates, typically made of a ceramic, and an array of thermoelectric material pillars we call elements. Through the Peltier effect, TECs directly convert a current and voltage supply to heat flow. TECs can be built in a range of sizes and form factors and are particularly well suited to cooling small components in constrained spaces where a vapor compression system simply is not feasible. Hence, their application to laser packages. In most cooled laser package designs, the laser diode assembly is mounted directly to the TEC. And the TEC is not only the thermal management device for the light engine, but also acts as a sort of optical bench onto which other sensitive optics components are attached. When the laser is powered on, the TEC pumps the heat generated by the laser away from the assembly and into the package base. To control the temperature to a specific set point, a PID controller reads the temperature from a thermistor mounted near the laser and supplies the needed voltage and current to the TEC to maintain a temperature set point. The TEC can also be powered in reverse bias and actually heat the laser to maintain operating set point in low temperature environments, typically below 0°C or so. Now, you may be asking why lasers and optical networking components need TECs or any active cooling at all. At high temperatures, several characteristics of the laser degrade, which impacts the transceiver's ability to maintain the specified signal strength and data rate. And suddenly, that 4K UHD stream of House of Cards becomes a choppy, pixelated mess of a video feed. First, laser wavelength shifts longer at higher temperatures. This shift can be large enough across the operating temperature range of the laser that it can actually cause major signal loss. This is especially true in applications like dense wavelength division multiplexing, or DWDM, where multiple closely spaced signal wavelengths are sent down the same fiber. In this case, a tech is required to maintain very tight control over the laser temperature and wavelength. Also, the maximum modulation frequency of a laser drops rapidly with increasing temperature, which means the rate at which it can transmit data is reduced. For most diode lasers, the maximum modulation frequency, that's a mouthful, also called the 3 dB cutoff frequency, is the frequency at which the magnitude of intensity modulation drops to half of the low frequency value. This cutoff frequency can drop by tens of gigahertz across the laser operating temperature range, greatly impacting the rate of data transmission. Laser power conversion efficiency is also reduced, which means that more electrical power is required to maintain the same optical power. So, for a given input power, signal strength and therefore reach decrease with increasing operating ambient temperature. All of these factors conspire to make temperature control very important for lasers used in optical communication, and TECs are really the only cooling technology that can provide the required cooling and temperature precision in these laser packages. There's a range of fiber optics products that utilize TECs for thermal control. TECs are integrated into many different types of laser packages, including TO cans, box TOSA, and butterfly, or also known as BTF packages. Those laser packages are then integrated into transceivers. Transceiver applications that utilize cooled lasers include QSFP28, CFP4, and CFP8 transceivers. Active cooling is almost universally required for tunable lasers, or ITLAs, as the tech provides the wavelength tuning by taking advantage of the same behavior I just mentioned on the previous slide, but in a controlled fashion, where changing the operating temperature of the laser tunes the laser wavelength. In addition, various flavors of wavelength division multiplexing, or WDM lasers, as well as the pump lasers for erbium-doped fiber amplifiers, or EDFAs, often require active cooling as well. If you describe these products in terms of data rate and reach, we have observed that slower data rates like 10 gigabit per second or lower usually only require active cooling for the longer reach applications, say in the 40 kilometer or more range. But higher data rate packages like 100 gigabit per second all the way up to 400 gigabit per second require cooling even for the shorter reaches down to, say, the 5 to 10 kilometer range. This has led us to apply our own kind of general rule of thumb that the higher the data rate or the longer the reach, the more likely the application is to require active cooling with a tech. Now I'll shift gears to talk about how the laser light engines inside optical transceivers are evolving. The plot on the left shows how package heat density has dramatically increased with the ever-increasing demand for bandwidth. So as the Netflixes, YouTubes, and Facebooks of the world drive the demand for more internet bandwidth, transceiver designs have shrunk very rapidly to fit more bandwidth per unit of rack space. And this leads to a dramatic increase in heat density at the laser package level. In working with our customers, we've noticed that the heat pumping requirement per unit area our customers are seeking has roughly increased by about 3x in the last 2 years alone. And we're also designing for more and more components that must support the wider -40 to 85°C operating temperature range, which is also called industrial temperature or ITEMP range. In addition, power consumption limits set by industry-wide MSA specifications impose strict power budgets on the transceiver and laser package. Since TECs are one of the larger power consumers in a cooled laser package, it's actually really important to consider heat pumping efficiency at multiple operating points when designing and selecting a tech for a particular laser package. All of these requirements are transpiring to pose a very challenging thermal environment for lasers. Looking forward to next generation package designs, lasers, detectors, and optics built directly into the board level will replace copper lines in a number of instances, and we expect novel packaging and cooling approaches will be required here. Also, non-hermetic laser packages are expected to reduce the cost and complexity of lasers, but introduce a number of cooling challenges mainly related to condensation in humid environments. So, I've shown how the trends in optical transceiver and laser packaging products are introducing new and more difficult thermal challenges, and those three main challenges are higher heat flux and temperature, reduced package power consumption, and new ways of integrating optics into networking systems. Now, I want to show you some ways we can tackle these challenges through design and thermal modeling, innovative materials and processes, the processes and components via which the techs are integrated into the lasers, and some new technology currently under development. But before going into gory detail about thermal design in these packages, I want to provide a general overview of a thermoelectric system. The system can be very simple and consists of the laser assembly itself attached to the cold side of the tech. We call that the accept side. The tech itself, and the heat reject system, which is typically, in these cases, the laser package base to which the tech has been mounted. The tech in this thermal system is controlled with a driver circuit, which uses temperature feedback to dial the tech power and maintain a certain laser diode assembly temperature. A tech operates most efficiently when the extraneous temperature deltas on both the hot and cold sides of the tech are minimized. One of the most important ways we can address the thermal challenges presented by new laser packages is by properly defining the requirements during the tech design process itself. So during this design process, our applications and thermal engineers work with laser package designers to fully account for all sources of heat and performance loss in the package. In the diagram below, you can actually see some of the characteristics we must consider. The active heat load from the laser itself is the most obvious one, but if we take the package to be at a temperature of 85 C and the tech cold side required to maintain the laser at 40 C, some additional heat sources and losses will pretty quickly become apparent. For instance, heat conduction through the wires that are connected from the laser assembly to the package sidewall, and heat convection add to the overall heat load that the tech needs to pump away from the laser. There are also additional parasitic temperature differences that are due to thermal resistance of the layers between the tech and the laser, and those mean that the tech has to get cooler than the laser temperature set point. So if the laser is being controlled to 40 C, the cold side of the tech may need to be at 35 C or even lower, depending on the design of that laser diode subassembly that's mounted onto the tech. As mentioned on the previous slide, the size of this delta is an important input to defining tech operating point and efficiency. So laser package designs should target low thermal resistances to minimize these parasitic delta T's. We take those aspects of the package design under consideration to create a first principles set of product requirements for every new application-specific tech design that we create. And you can take this even a step further, where our customers have supplied their own package CAD to us. And we utilize that package CAD and create a full 3D thermal model that completely accounts for all of the additional heat sources and temperature gradients. This allows us to make sure, one, we're designing a tech specific to this application to achieve the best efficiency possible right out of the gate. Two, it allows us to accurately predict tech operating conditions and reduce the amount of time spent respinning designs. And then three, we've even actually provided insight into the package designer how they might reduce thermal parasitics, which in turn reduces overall package operating power even further. The materials and processes that go into fabricating techs can also have a big impact on laser package thermal properties. If you look at the anatomy of a thermoelectric cooler, there are several ways to improve performance, even while reducing both form factor and power consumption. First, an ideal tech uses a thermoelectric material whose elements can be made incredibly thin and packed very tightly within the device to enable very high heat pumping densities, but not sacrifice efficiency. A high-performance tech may also utilize thin ceramic substrate materials to reduce the thermal resistance of the tech and increase the maximum DT achievable at a certain overall tech thickness. Third, a high-performance tech requires extremely low contact resistance to the thermoelectric material elements. It turns out that electrical resistive losses at these interfaces end up limiting the performance of thin and small techs. At Phononic, we have all of these design options at our disposal, and they, along with our proprietary manufacturing process, comprise our PicoTech device platform, which enables performance not previously available. So what does that mean in terms of real-world tech performance? Well, in relation to the challenges that I've highlighted earlier, increased heat pumping density in a smaller form factor and tighter power consumption requirements, we can offer advantages for both metrics. From our research and from direct customer feedback, our tech designs can provide up to a 60% improvement in heat pumping capability per unit area and about a 25% reduction in tech power consumption. These two advantages can compound to provide big real estate savings inside the laser package, as well as reduce the overall laser package power consumption in the most thermally demanding applications. Now, tech and laser package design are important to ensuring optimal performance, but the processes and components that the tech is integrated with can have just as much impact. So like all thermal interfaces, the quality and thickness of the interface between the tech and the laser package base can have a big influence on tech performance. For instance, if you choose a solder or a thermal epoxy, the reflow or cure temperatures and overall package processing thermal budget can affect the thermal conductivity, percent voiding, and thickness, which directly defines the thermal resistance of that interface and can greatly increase both the tech-to-package delta T and the maximum amount of heat pumping that is possible within the package. So characterization tools like X-ray or CSAM, also known as confocal scanning acoustic microscopy, can be used to inspect these buried interfaces and provide non-destructive feedback on the interfacial quality and how it may change throughout the laser package assembly process. This slide shows CSAM scans of a tech-to-package thermal interfaces. The top line of images shows how improper choice of solder that cannot withstand extreme temperature processing can degrade the thermal performance and degrade that thermal interface. The tech controller and driver used in the next higher assembly, which is called a transmit optical subassembly or TOSA, can also have a large impact on overall tech and package power consumption, especially if the wrong driver is chosen that does not align well with the tech operating point. There are several tech driver solutions available in the market today, and I've shown some examples from Analog Devices, Maxim, and Linear Technology here on this slide. Like most driver circuits, the efficiency drops rapidly at the low end of the operating range. So you definitely want to stay in the higher current range of this operating efficiency curve. But at the same time, the efficiency increases with higher tech load or higher tech V over I. So we recommend that the expected typical tech operating point is actually used to help select the best tech driver for the package, or vice versa. Use those efficiency curves to help inform the design of the tech for your package. Also, we recommend PID control instead of PWM to maximize tech heat pumping efficiency. We are also working on a couple of technologies to address the next generation of optical networking components. One tech platform under development enables cooled, non-hermetic packages. This moisture-resilient thermoelectric device avoids corrosion issues associated with condensation. However, it's still recommended for low humidity environments only, and careful package design must allow for a sort of breathable exchange of air and moisture with the ambient environment. If the tech cools the laser assembly below the dew point of the environment, there's a high risk of condensation on the laser and optics themselves, which will likely interfere with fiber alignment and lead to optical coupling losses. In fact, at typical data center and humidity laser operating temperatures, it is highly likely that the cold side of the tech will condense water out of the environment. So beware of the dew point of your customer's operating environment when designing a cool, non-hermetic package. Another potential technology opportunity is a more tightly integrated tech and laser package. This is particularly advantageous to TO CAN laser packages. Cooled TO CAN packages are very small. A TO56 header typically has less than a 4 millimeter diameter area to integrate all of the components necessary for a high-speed modulated laser. As such, these packages are incredibly space constrained. So any approach that reduces the overall real estate required for cooling can help the package designer integrate additional optics, modulators, or even photonic ICs that previously just couldn't fit inside the package. Conversely, this approach can pack even more cooling into the same space to support extreme thermal requirements. In addition, this technology translates to fewer process steps and a simpler BOM for the package manufacturer. So to summarize what we've talked about today, increased data rates and reduced package footprints are conspiring to create an increasingly challenging thermal environment for lasers and optical communications. Thermoelectric coolers have been used in this space for decades and are still really the only technology that can achieve the stringent cooling requirements of fiber optic laser packages. However, Phononic's design approach and high heat pumping density, low power consumption techs offer advantages that align well with these tougher thermal challenges. Also, package integration choices such as the tech driver chip, solder selection, and process thermal budget should be made very carefully to achieve optimal tech performance in the end product. With that, I'd like to thank ThermoLive and the audience for the opportunity to talk today. Thank you.
Excellent, Alex. Great presentation. Lots of coverage, and I appreciate the background and the primer stuff that you provided as well. And I'm sure a lot of the audience did, because some of the audience wasn't necessarily familiar with this technology to begin with. But we will be taking questions now. So if anyone would like to throw up any of the questions they have, anything they've puzzled over, we even had a few of the audience members ask questions before the presentation even began. So I think a lot of people are really excited to hear from you about this, Alex. We do have a lot of questions, but we also have a lot of time to cover them, so that's great. I'll go ahead and hit up the first question. And this one is about the maximum operating temperature of techs, and if there is a really high temperature availability, a high max temperature device availability. Someone suggested in their question around 125 degrees C of continuous operating temperature.
So that's the question about the package ambient, or the tech ambient that it's working in?
Yeah, it's ambient, and I'm assuming it's max operating temperature as well. if there are product lines that
Yeah.
can fit that.
Yeah, so we typically, spec our techs to operate in a 85C max ambient, but we encourage our customers to push the boundaries, and 125C is definitely we test to that in storage and in operating conditions. So it's definitely doable. We've got testing beyond 2,000 hours and power cycling for many thousands of cycles at that temperature range. Our spec sheets say 85C, but even with the current technology platform that we're working with, depending on the application, 125C may be doable.
Excellent. Thank you for illuminating on that one, Alex. Now the next question, and I believe you covered some of this in your presentation, but I think some of the folks on the webcast would appreciate this illuminated a little bit more. It's the value of a tech in between the laser and the package. So the question revolves around the benefits of having the tech there, or just having the laser plate directly against the packaging plate. And say, for suggestion, if the packaging plate were a cold plate, so instead of using a tech, what would get the best performance, and are there reasons why you'd go to a tech over doing just that simple passive setup?
Yeah, so I think the best way to answer that question is really to kind of talk about temperature, lag time in the temperature variation. So you would need and the space constraints that there are in these packages. So these laser packages are, all totaled, maybe 10 to 20 millimeters on a side, and only a couple of millimeters thick. And then they go into this transceiver assembly that is, it's basically 8 by, I think, about 20 millimeters in cross-sectional area, and only about 70 millimeters long. And then they're densely packed into a rack unit to provide very high, bandwidth density in a data center or in a, ISP location to transmit and receive data at incredibly fast rates. So one is space constraint. There just really isn't room to provide cold blocks or water cooling to each of these transceivers. And two, these lasers require, essentially instantaneous or response to fluctuations in the heat load, and that's what the thermoelectric devices can provide.
Excellent. So a lot faster response to the heat flux than a passive technique. Just a cold plate.
Faster response and much more aligned with the space constraints that these products have to deal with.
Excellent. Thank you. I hope you answered the person's question. They seem pretty excited to hear about it. The next one has to do, I'm assuming, with the gaseous environment around a tech. The person suggested that a lot of data sheets on techs are generated in either nitrogen or vacuums, and that's how their cues are generated, the first cues are generated. And how can you translate information taken under those circumstances to, for example, a CO2 environment by comparison? And the questions around the first and second cues and how those are generated, and if there's a way you can communicate that from one gaseous medium to another.
Yeah, so we actually, I don't know how specifically CO2 compares to vacuum or nitrogen. We typically, when we do the performance modeling, we actually, for our customers, we actually model the gas that's inside the package as part of that model. So it's basically taken into account as a parallel thermal resistance. And that's how we actually get that built into our model.
So if someone were to reach out to you, you'd be able to provide them with information for their specific environment.
Absolutely. Yeah.
Okay.
Yeah. In fact, we frequently have customers ask to compare the performance of the TEC in, these are, like I said, hermetically sealed and it's in an inert environment, but they'll ask us to compare xenon, argon, nitrogen. They want us to provide the different operating points for those different ambient gases.
Excellent. Great. So in terms of solder materials, when someone is asking what are the recommended solder materials, types of solder, or conditions that you might need to attach the tech to the plate and the laser?
Yeah, good question. It's really dependent on your own package requirements and really what you're doing downstream of the tech integration step. We've seen customers use, I will mention that an important requirement of some customers is no outgassing of whatever medium they use, so they try to shy away from fluxes. Fluxless bismuth tin preforms is a one we see pretty commonly. We see SAC 305 as a common attached solder used for these type of devices. We actually also see thermal epoxies used pretty commonly. And if thermal performance and tech power consumption performance is really, really important, we tend to try to steer customers more towards the solder than the thermal epoxies, just due to the better thermal interface that can be created. But yeah, those are three really common examples that we see out in the field used by our customers.
Excellent, excellent. On to the next question. This person is asking if there are flowtherm.pdml smart part files for these devices. Do you provide those?
No, we don't. So we have a proprietary model that we've developed in-house that we've kind of built a hybrid modeling platform that interacts with Flowtherm and some of the other modeling tools that we have out there. So we don't provide that model, but we are very happy to work with customers to generate the modeling that is needed under NDA, of course.
Excellent, which might be a better answer than, yeah, we just have generic models.
That's right. And really the purpose of that is to, it kind of goes into our design process where we want to make sure, the right design and the right, kind of from a sizing perspective, the right device is used, and we want to help the customer with that. So that's how we typically will run our modeling efforts. We'll do it in conjunction and in partnership with the customer.
Actually, that is a great point because the next couple of questions are about that design process. And someone else asked about how it actually helps with shortening the thermal design guidelines, and if you could provide some examples. So I think there's a lot of interest in exactly how you guys at Phononic help with that.
Yeah, so we've actually, so I would say this, and I'll provide the general and then the specific examples. When we approach a customer or a customer approaches us, we can ask for a specific set of requirements, including heat load and things like that. But we tend to back it up, and say, all right, hold on, let's get the active heat load from the laser. Then you can tell me how many wire bonds are to the cold side of your device, and how long are they? What diameter wire? What's the material? We go into very in-depth conversations. And that's kind of that first principles approach that I was talking about, where we want to hear, all right, what's your package design like right now, and what are you trying to accomplish, and we'll get you a design that works best. And a perfect example of shortening that design cycle is we had a customer approach us that said, look, we bought these devices from a competitor, and we're getting thermal runaway issues where they're not able to cool sufficiently for the application before the hot side temperature starts taking off. And what we found in working with them, and this is a great example of where them supplying us their package CAD was really helpful. We did a full thermal analysis for them and found that there were some heat loads that hadn't really properly been accounted for. And so the tech itself was severely undersized for the application in terms of heat pumping capacity. And so, I think in that case, the shortening of the design cycle was, we would have eliminated that first unsuccessful loop had we been able to do that in-depth design a little more early in the process instead of them just going out and buying techs. So I think that's it's a little bit of making sure we ask the right requirements questions at the outset, and a lot of design due diligence to make sure we're accounting for everything in the package.
Excellent. So this question is kind of about what you end up giving to a customer so that they can maybe verify in their simulations if the tech is a good solution. They're wondering if you don't provide the flowtherm.pdml smart parts, do you provide Qmax information, Tmax information, V curves, that kind of stuff? What would you end up delivering to a customer after you guys did your evaluation?
Yeah, so what we typically deliver is a full design proposal that can include some performance modeling tools that we provide. It's typically not a Flowtherm model, but we can provide some calculators for different operating points and things like that. But also, at the very beginning, when we are talking with the customers, we're asking things like, all right, what is your laser diode assembly temperature? What are all of the layers in between the laser and the TEC? How are you attaching it? We ask a ton of questions to then, with that design proposal, we deliver a performance model for the operating points of interest that the customer intends to run at. And in particular, those operating points are usually kind of the boundary conditions, like max operating temperature range and kind of the coolest the laser will need to be cooled in the application. So we kind of provide those boundary conditions and then a more typical operating condition. And so lots of, at that proposal stage, lots of performance information, and we can work with the customer to provide, additional models that are a little more free form as well.
Thank you, Alex. Excellent. Now, just to give you a heads up, there are a lot of questions, and some are still coming in. So we're going to try to go through as many as we can before time's up. We do only have a few more minutes, so I did want to let you know that before we dig in. And these are great answers, great responses, and I'm sure the audience is pleased.
No problem. And I just wanted to let the attendees know that I'm happy to follow up via email afterwards to provide some more answers if they don't get answered in the time allowed.
Thank you. Excellent, Alex. The next question is about, and I think you already touched on this a little bit when you answered the solder question, is what thermal interfaces are most important in these packages?
Yeah, that definitely basically the interface between, basically on either sides of the tech. That cold side interface is important because it can be, it can be very definitive in terms of heat spreading and the amount of delta T between the laser and the tech. And I mentioned in the slides, but not verbally, thermal shorting. If there are any components, large surface area components that directly bridge the hot package sidewall to the tech cold side, that's basically a thermal shunt resistance. So understanding those interfaces, both in one dimension and two dimensions, is really incredibly important. And that hot side interface is also incredibly important, because if that hot side interface is badly formed, if there's a high degree of voiding, you'll end up with tech hotspots that could not just impact performance, but could impact long-term reliability. And also, if it's too thick, you're not going to get the expected performance, because your hot side will be getting too hot, and your delta T will need to be larger than you had previously modeled. So really, those hot and cold side interfaces are the most important, and the ones you want to make sure you engineer very carefully.
Great. Now this has some relevance to that. I think it's a little bit more of a basic question involved in that, and that's, why is minimizing delta T in the package important?
That's a very great question, and it's actually it is related to how techs work. So unlike other heat pumps, say vapor compression systems, techs, the COP of a tech is very dependent on the delta T across it. So at a set hot side temperature, the lower the delta T across the tech, the higher the COP, the cooling COP will be. So you want to make sure you get that, if you're designing for a 30 C delta T application, meaning 30 C between ambient and the laser, you want to make sure that tech is at the delta T across the tech, because it's going to be larger due to those thermal resistances. You want to make sure that tech delta T is as close to 30 C as you can get. And it's just, like I said, just due to the dependence of COP and how it increases with decreasing delta T.
All right. Excellent. Now we only have a couple minutes left, but I think we can go over a little bit. We have a ton of questions left as well, and they're all really good questions. I'm also very interested in hearing these answers. But we'll just go to the next one, and if we can't take the rest, we'll talk about that in a bit. The question is, why does PID control maximize cooling efficiency? The person who asked the question says, I thought the purpose was to control the temperature within a narrow range. So what is the meaning of efficiency in this context?
That is also a good question, and it's actually, again, related to the behavior of COP for thermoelectric devices. So if you were to plot the COP curve as a function of voltage or current, of tech voltage or tech current, you would find that it's got a pretty well-pronounced peak at a slightly lower voltage point. Well below its maximum rating, right? So what you want to be able to do is operate that TEC in both a high heat pumping mode and a high efficiency mode. So you could conceivably size the TEC to operate at that high efficiency mode, even with only at its max PWM voltage, but you will sacrifice that higher heat pumping capability for those, rare extreme temperature conditions that you need to support. So it's really about properly sizing the thermal system to be able to allow the tech to operate at both that high heat pumping mode or high delta T mode and a more kind of low power maintenance high efficiency mode. And the PID controls that are used are plenty good enough in these cases to provide very, very tight temperature control in the application here.
Wonderful, Alex, and thank you again for the phenomenal presentation and your answers. And there's many, many more questions in here, and I want to thank everyone else for joining us as well. And don't worry, if your questions weren't answered on the presentation, they will be answered and available on the ThermoLive website. So even if we didn't get to them today, they'll be addressed. And obviously, Alex is also very welcoming of being able to answer those questions personally also. Again, do want to thank Alex for giving so much information today. And there will be an email link of the on-demand version of this presentation within 24 hours. So if you logged in a little late and you missed the beginning, or you'd like to refresh it again or show it to your colleagues, you'll be able to do that. And lastly, I'm JJ DeLille, and thank you for attending ThermoLive 2017.
Thank you, everyone.